All, welcome to the 64-bit edition of the Security Tube Linux Assembly Expert course and certification. Now in this video, we will look at the very interesting bit shifting instruction set. So the first instruction we will take up is shift left or shift arithmetic left, both of which do the same thing. Now, as you will see in bit shifting, the carry flag has an interesting role to play in most of the instructions. So let's say that this is the initial state. You have the carry flag and you have an operand, and after that you issue an instruction to shift left by 1 bit. What happens then is that the most significant bit which is there of the operand is replicated into the carry flag. So in this case it was 1, so we basically got 1 in here when we shifted left by 1 bit. The least significant bit is automatically put in as 0, right? So let's look at a live example to understand this better. You can download bitshifting -64.nasm from below the video. So here is the code, right? And what I'm going to do is, let me just open this in a new tab so that we can follow as we go. And I could probably put bitshifting.nasm, open read only. I can go back in here, close this, and go ahead and use nasm to assemble, ld to link, and then our good friend GDB to load this up. Set the disassembly flavor to Intel, break on start, run it, lay out the assembly, lay out the registers. So the very first instruction in here is really moving in this large number with the most significant 4 bytes all zeroed out, and then the least significant 4 bytes all ones. That's why you see all the FFs in here, right? Now as you can imagine, if we first shift arithmetic left by 32 bits, then what would happen is these zeros in here would actually get shifted out. The carry flag, of course, given that all the values being shifted out are zeros, would continue to be 0. And after the 32-bit shift is done, we will basically see that all these FFs become the first 4 byte of the first 4 most significant bytes, and then you have zeros filling up their place. So let's go ahead and do the following. Step I, this loads the value inside RAX. Great. Shift left by 32, and as you will clearly see, if you notice, we have the flags in here. The carry flag is not going to be set after the operation. You will see that. And there you go, right? If you notice, now the FFs got shifted into the first 4 significant bytes, while the least 4 significant bytes got filled up with zeros, and the carry flag was not set simply because we just sent out all the zeros. Now if we shift left by 1 again, then the most significant bit currently is 1, and that gets shifted out into the carry flag. So the carry flag would be set. So let me hit a step I, and there you go, right? The carry flag gets set, as you can clearly see, and of course this value would change to reflect that 1 bit going out. Now the instruction CLC is basically clear carry. So when we hit that instruction, the carry flag would be cleared. And there you go. Now let's look at the second instruction set, which is shift right. Now in shift right, the principle is again exactly the same, but now you would have to basically visualize the carry flag on the right hand side, or basically the least significant bit, if we do a 1 bit shift right, would be replicated inside the carry flag, right? While 0 would be inserted on the most significant bit side. So let's go ahead and try this command out. Again, very simply, first we are going to move this value inside RAX. Let's do that. Now we shift right by 1, but in this case, the LSB is actually 1 already, which means when we shift right, the carry flag would be set. And there you go, the carry flag is set. Now, if we go ahead and shift right by 31 more bits, as you can clearly imagine, the value in the RAX register now would become a 0, and of course the carry flag would still be set because the last bit which got shifted out was still a 1. Now let's clear the carry flag again with a CLC. There you go. Now the next instruction basically would be shift arithmetic right. So let's go back to the slides. Now shift arithmetic right is very interesting, right, and can be confusing, so pay special attention. Now in the case of arithmetic right, the behavior is different when we have a positive operand versus when we have a negative operand. Okay, so let's look at the positive operand case first. So this is a positive operand. You can clearly see that, the sign bit is 0. Now when we do a shift right by 1 bit, the LSB, the lowest significant bit, really is actually gone ahead and replicated inside CF, while because it's a positive operand, a 0 gets filled up in the most significant bit. Let's go ahead and verify this. So I'm going to load our familiar value again in RAX. Now it's a positive value. I'm going to shift right by 1. Of course, because the LSB right now is 1 currently, when we shift right, the carry flag would be set. However, because it's a positive value, the most significant bit, the leftmost bit, will be 0. And we can clearly see that, right? Let's clear the carry flag again. And let's basically look at what is going to happen when we have a negative value and we do the same thing. So let's go back to the slides. Now let's assume the operand is negative. As we can see, the sign bit is set. Now when you do a shift right by 1, then what happens is, of course, the state of the least significant bit is replicated in the carry flag, but because it's a negative operand, 1 gets put in as far as the most significant bit is concerned. So let's verify that. So move this value in. Let's shift right by 1, but remember now it's a negative value. So the carry flag will be set, but 1 will be moved in, which would ensure that the value of RAX doesn't really change. And we can clearly see the carry flag is set and RAX continues to be identical to what it was because 1 was moved in for the 1 bit which went out in the most significant bit, which basically did not change the value of RAX as a whole. Fantastic. Now, the next series of instruction is rotate instructions. I'm just going to look at one of them, ROR, and basically you have ROL. I'm sorry, there is no LOL. There's RCL and RCR, which you can look up yourself later on. So rotate instructions are very interesting, is that they do not discard any bits anywhere, but rather rotate the bits around in the register, right? So let's go back in here, and I have a very interesting formation: 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So at first, let me go ahead and rotate this by 8 bits, right? 8 bits would really be rotating it by 1 byte, which would mean the value EF at the very end would rotate and come here, and everything else would shift. So we've moved this value into RAX, and now I'm going to rotate by 1 byte. And as you clearly see, EF is now in the front and everything else shifted accordingly. Now, if I'm going to shift by 12 bits, let's basically see what happens. This is something for you to guess. And again, the formation changed. And of course, now to adjust everything, right? If you want to basically go ahead and get it back to the same formation, then you have to ensure that the final rotation is for a value which basically compensates and everything adds up to 64. So 44 plus 12, 56 plus 8, 64. Now when we rotate now by 44 bits, we would basically come back to the same old formation where we were before. And there we go. Right? How the carry flag changes, I leave that as an exercise to you. It's very simple to figure it out. Of course, after that, we just have our exit syscall, which we can continue. There you go. So hopefully you found bit shifting, rotation, and all of that interesting. This is something which can come in really very handy. So keep this in mind. That's all I have in mind for this video. If you're enjoying all of this at Pentester Academy, we would really appreciate if you can recommend us to your friends and colleagues in the community. That's all, my friends. See you till the next video. Bye-bye.